Welcome on know. In this one, I'm going to give you a bit of motivation behind the concepts related to partial fractions. Bit of motivation for partial fractions. That's our objective here. Keep that in mind. So let's go through that process. So imagine I have this simple expression, like 1 over x plus, for example, 2 over x minus 1. To understand partial fractions and the motivation for the concept of partial fractions, you want to begin with something more familiar. Whenever you study math, you want to begin with something hopefully more familiar. So if I begin with this, and I know how to add rational expressions like these, then that concept can then essentially be reversed, and we call that partial fraction decomposition. That's all it is, okay? So here, I have 1 over x plus 2 over x minus 1. What I really need to do is have the same bottom, correct? So for that reason, what I'm going to do is I'm going to multiply as follows. I'm going to multiply 1 over x by x minus 1 over x minus 1. So when I carry the process out, it's going to look like this. It's going to be x minus 1 over x minus 1 times 1 over x. Okay, being very detailed here. Now that 2 over x minus 1, and the bottom, it's missing an x. Now you have to be careful what we mean by that. We mean there's an x missing that is just by itself as a single factor. The x that you see in x minus 1 over here, where I've just highlighted, that's not the same x. That's a different x because it's attached to the negative 1. Okay? So that means over here is going to be 2 over x minus 1 times, for that reason, x over x. You see? Now x minus 1 over x minus 1 is a form of the number 1. X over x is also a form of the number 1. So let's continue simplifying. Notice that when I look through my expressions here, I see that now they both have an x minus 1 in the bottom, so I can put everything over the same denominator of x times x minus 1. Okay? Next, in the top, what I have then is the following. I have this 1 over here. So this 1 times the x minus 1 right here, see? So when I multiply them, it's going to give me like something that looks like 1 times x minus 1. Okay. Now for the second one, I have this 2 up here times the x. That's going to give me a 2x up there, you see? Now continue with this process. You're going to have 1 times x minus 1. So let me copy the bottom. It's already the same thing. It's just x times x minus 1. But in the top, I have 1 times x minus 1, which is just x minus 1. And then you attach that 2x. Okay, lastly, combine the terms in the top. So when I do that, it's going to give me x plus 2x, which is 3x, and then minus 1. And in the bottom, I have x times x minus 1. So this expression, 3x minus 1 over x times x minus 1, is what we generate from adding 1 over x plus 2 over x minus 1. We're adding those two, we're generating that. So the real question is now, can this be reversed? And the answer is yes. We call that partial fraction decomposition, okay? So what I'm going to do is proceed as follows. I'm going to now instead begin with this expression. Okay, let me put that over here. 3x minus 1 over x times x minus 1. And I'm going to decompose that into 1 over x plus 2 over x minus 1. The key step is to recognize the following. Look back at the original expression. 1 over x plus 2 over x minus 1. There's a 1 and there's a 2. There are two constants. And in the bottom you have an x and an x minus 1. Do you see that? Now, though that x and x minus 1, if you look now above my head, it's also present in that form, isn't it? As two factors. Each of those specifically is what we call a linear factor because it's x to the first, and the x minus 1 is also actually to the first. Okay? We don't write those, but that's what it's implied to be. In other words, if I wanted to be very formal, I could put a little exponent of 1 up there, and I could put a little exponent of 1 up there. And then the x is a linear factor, and x minus 1, because it's raised to the first, is another linear factor. So the decomposition step will go like this, okay? Beginning with the motivation up above for adding them, you would basically assume that there are two constants that look like this. A over x plus, and then here b over x minus 1. I understand perfectly this is a rigged example, okay? But the logic is what matters. And I designed it this way on purpose because I want to show you how the steps pretty much reverse. Okay? So you have a over x plus b over x minus 1. And again, you're going to pretty much assume that you can combine the right side just the way you combine anything else. So it's going to be like a times x minus 1 basically plus b times x over that x times x minus 1. See that? If you look at the step above my head here, you see how it's very similar to that step where it says 1 times x minus 1 plus 2 times x. Now look at this step. It's a times x minus 1 plus bx over x times x minus 1. It's the same step essentially. The only difference is clearly the a and b are not known in this example. Okay? So then you continue. Combine like terms in the top. Keep the bottom copied this whole time. So it's ax plus a, or rather minus a, and then plus bx. And this whole thing is hanging here over, okay, ax times x minus 1. And now compare these two. So what I mean is, let's see, compare this 3x minus 1 in the box and compare the ax minus the a plus the bx in the box. The bottoms are already the same. They both have an x times x minus 1, so you don't have to worry about those anymore. The key then is to just equate the numerators. So you can find the a and the b. That's it. Okay, so let's work this out right here. I'm going to proceed as follows. So big idea at this point is equate numerators. So in other words, 3x minus 1 should be equal to ax minus a plus bx. The only way two polynomials are equal is if they are equal coefficient by coefficient by coefficient. Now when I look at these two, on the right side specifically, let's say right here, on the right side I have a bx and an ax. I need to gather the x's together. So it's going to be next 3x minus 1 is equal to ax plus bx. Oh, slow down, bx. And then this is minus a. So now, on the right side, the left side stays. It's already fixed because we know it's 3 and 1. But on the right side, factor the x is going to give you a plus b minus a. See that? Now, what we can do is equate matching coefficients. What does that mean? Well, you see, on the left side, the coefficient on the x is 3, and on the right side, the coefficient on the x is a plus b. So, in other words, you're going to write a plus b should be equal to 3. Also, on the left side, we have negative 1 as the constant. On the right side, we have negative a. So, basically, set negative a equal to negative 1. You see? Just match them in pairs, essentially. Now, here we are lucky because negative a equal to negative 1 is easy to solve, right? Simply just divide by negative 1 on both sides. So, a will be equal to 1. Once you know that a equals 1, just plug it into a plus b equals 3. So it's going to give you 1 plus b equals 3. And then you just subtract 1 from both sides naturally enough. And it's going to tell you that b is equal to 2. Okay, so b equals 2. Now obviously we already know this is true because this is a whole, completely rigged example. But it gets the idea across. So over here now, what I can claim is the following. That this expression, 3x minus 1, say, over x times x minus 1 can be decomposed into two separate fractions that look like the following. 1 over x and then plus b divided by x minus 1. So this is hopefully giving you some insight into the motivation for partial fraction decomposition. In other words, think how to reverse adding or subtracting rational expressions. That's a fundamental concept, okay? All right, thank you so much. Please leave a like and subscribe. I'll see you in another video.